Hey guys, in this video, we're going to go over some data structures like disjoint sets, heaps, and hashes. We're going to have another video going over the second half of data structures. So yeah, with that being said, let's get right into disjoint sets. So what is a disjoint set? A disjoint set is a public interface. This basically means that if we were to make a new data structure, we could implement disjoint sets, and it's going to inherit all of these handy-dandy methods that we have. The first one is connect. It's going to take your two parameters and connect them. The second one is connected. It's going to take those two parameters and return a Boolean after checking whether they are in fact connected or not. So there are four types of disjoint sets. The first one is quick find. Quick find uses an array of integers to track which set each element belongs to. So this example here shows that there are three sets. Each set is denoted by curly brackets. So the numbers in each set of curly brackets are connected. So if we were to run is connected on, let's say, 1 and 3, it would return true because they're in the same set. But if we were to run it on 1 and 0, for example, it would return false because they're in two separate sets, so they're not even connected. One little downfall to quick find is that it's really hard to figure out which one the parent and the children are. We just know that they're connected in some way, shape, or form. So to improve on quick find, someone came up with quick union. This actually stores the parent of each node rather than the set they belong to, and it merges sets by setting the parent of one root to the other. There are two noticeable differences in the array representation of quick find and quick union. The first one is that it's all in one set of curly brackets. Unlike quick find, this doesn't necessarily mean that all of the elements in that set of curly brackets are connected to each other. There might be multiple sets in this one array. The second one is that there's positive and negative numbers. So what does that mean? Well, we know that the array representation of quick union is storing the parents of each node. This means that the numbers we see here are not the only numbers we're actually working with when we're trying to visualize and make the disjoint set. The actual numbers that we're working with are the indices. So the values in each index are basically telling us that, hey, this value is actually the parent of whatever index it's in. With that in mind, we know that -1 is not an index value. So if we have -1 in a index slot, that's basically telling us that that index does not have a parent. So if it doesn't have a parent, then we know that that index is going to be the root. Another cool thing about this is because we know that negative numbers are now roots, if we see multiple negative numbers in this array representation, we know that there's going to be that many sets. Because if you have two separate roots, then you know that those two roots are not connected at all. So in this case, we have two negative numbers. So we're going to have two roots or two sets where one root is going to be 1 and the other root is going to be a 3. Moving on to weighted quick union. This basically does the same thing as quick union, except now it's deciding which set is merged into which one by size. This is because we want it to reduce stringiness. So we want the larger set to absorb the smaller set, and we want to compress it as much as possible. Because if it's a long and stringy set, we're going to have to traverse for longer, and it's going to mess with our runtimes. The only difference in the array representation between quick union and weighted quick union, if it's a root, it's always going to be -1. But now because weighted quick unions is so dependent on size, we actually want to know what the size of each set is when we're looking at an array. So the number next to the negative sign for the root indices is actually going to tell us how many elements are in that set. So because we have two -3s in this array, we know that there's going to be two sets at roots 1 and 3, and each set is going to have 3 elements attached to it. The last one is weighted quick union with path compression, which sets the parent of each node to the set's root when we call find on it. This is basically telling us that when we call find on something, we're going to traverse up into the absolute root, and that's the number it's going to return. And if we're trying to connect to different ones, then we're going to have multiple new root connections. So now that we know what disjoint sets are, we're going to do everyone's favorite, which is asymptotics. This graph is pretty heavy. We have the 4 disjoint sets that we just learned, and we have different runtimes for constructors, connect, and is connected. Take a picture of this, put it on your cheat sheet, tattoo it on your body, ingrain it into your brains. You never know when something like this is going to come up on a test, and I think this is something really good to have on hand just in case. Moving on, we're going to go over heaps, or as I like to call it, leapfrog. What is a heap? There's two types of heaps: min heap, where every parent is less than or equal to its children, and we have max heap, where every parent is greater than or equal to its children. So looking at this diagram, what kind of heap do we think it is? Yes, great. Love the answer. It is in fact a min heap. So just like we learned in disjoint sets, heap sets also have array representations. So how do we get this heap diagram into its array form? The first step is setting the zero index as null. The second step, we're actually going to do something called a level order traversal, which is a type of tree traversal. What you do is you go level by level and continue adding the nodes you see into the array from left to right. So let's go over it. We're going to start at level 1, left to right. It's just a 1, so we're going to add that into the array. Now we're going to go to level 2, left to right. We're going to add the 2, then the 4. Then level 3, we're going to add 5, 3, 7, 8, and that's all it is to make the array. Another cool thing about heaps is it's really easy to find the index of the parent. All you have to do is take the index of the child and divide it by 2, and that's the index for the parent. Lastly, heaps are really useful because they can be used to implement priority queues. You might have seen this in heap sort, where you pop it off from the top root node. This is really good for priority queues because based off if it's a min or max heap, you already know the type of number, if it's going to be the smallest or the biggest, all the way at the root. So it's really easy to pop it off from the top. So we got into what heaps are. So how do we actually insert elements into it? Well, this is a fairly quick process. You just have to remember a couple steps. The first step that we want to do is we actually want to figure out what kind of heap this is and make our array from it. So this is going to be a min heap, so we keep that in mind, and we make our array. So set our zero index to null, and then we're gonna level order traversal it. So the array is gonna look like 4, 5, 6, 8, 9, 7, because we went top to bottom, left to right. This is what our array is going to look like. So to actually insert the element into the heap, what we want to do is append it to the end of the list and add it at the end of the heap. One thing to note, if we change something in the heap, we want to reflect that change in the array and vice versa. This is because they are representing the same object. So we want them to constantly be equal, because if we were to try and redraw the array as a heap or turn the heap into an array, we want them to be the same thing. After we add the element, we want to check if the element satisfies the heap condition. So in this case, since we're working with a min heap, we want to check if the parent of the element we just inserted is less than or equal to it. So we're going to ask ourselves, is 6 less than or equal to 1? And it in fact is not. So our good old friend Leapfrog is going to come to us, and it's going to ask us to play with it. And it's not going to leave until we do. So we're going to play Leapfrog. We're going to have one jump over the 6, and they're going to swap places. And remember, whatever we do in the heap, we do to the array. So we literally took 1s and 6 in the array, and we swapped where they were. Now we're going to ask ourselves the same question, and we're going to continue with this motion until we determine that no more swaps have to be made. So we're going to ask ourselves, is 4 less than or equal to 1? It in fact is not. And look who came to play again. Leapfrog's back. So let's play Leapfrog. 1 leaps over the 4. They swap places, change it into the array. We're going to ask ourselves one last time, are there any swaps that need to be made? Well, 1 is already at the root, so it has no parents. So let's double check to see if its children are satisfying the conditions. And 1 is in fact less than or equal to both 5 and 4. So that's it. Leapfrog's done for the day. It got tired. Just kidding. Leapfrog is back because asymptotics are a big deal. So let's go through it. We have 3 operations: insert, find min-max, and remove min-max. And there's a worst and best case for each of them. There's a couple quick ways to remember this. Find max is always going to be constant, and the best cases of all of these operations are also always going to be constant. You could think of it like if we're inserting a new element and right off the bat there are no swaps that need to be made, it's in constant. You didn't have to do anything else. Same thing from find min-max and remove min-max. If you want to find and remove it and they so happen to be all the way at the top of the root, that's all you have to do. You find it, you don't have to traverse. You remove it, you don't have to traverse. And the worst case for incident and remove min-max are log of n. Cool. That's it for Leapfrog. We played, we exercised a lot. I'm a little hungry. Let's get into hashing. So what's hashing? Hashing is really cool because normally we'd have to actually iterate through a data structure to find an element, but with hashing, we could actually go straight to it. This is because we use a really cool thing called a hash function. Unlike other data structures where when you are trying to add something to, let's say, an array list, you don't really have to think about what's happening behind the scenes. You just know it's being added at the end. Hashing is different because we use something called the hash function, which is a mathematical formula to determine exactly what bucket the hash function is going into. So to use the hash function, we basically have to find the hash code of our object and modulo it by the bucket size. And that's going to give us the exact bucket that the element's going into. The downfall to this is there could be a lot of collisions and overflow entries that come from this. Because let's say a bunch of elements have the same hash function. That means they're all going to go into the same hash bucket. So to solve this, we use something called external chaining. You could think of it as having a linked list type structure inside each bucket. So if we have multiple elements in the same buckets, they go in the same buckets, but they're kind of chained with each other. It's kind of like a linked list inside. Another downfall to this is what if all the buckets are filled? How do we prevent that or how do we fix that? Well, there's something called resizing with load factor. Load factor could be a predetermined number. And what you do is you take the number of elements and divide it by the number of buckets, and you compare it to the load factor. So if that is greater than or equal to the load factor, you know, hey, it's time to resize. So we usually resize by increasing the number of buckets by usually double. We don't want to increase it by more because then we're going to have a lot of empty buckets. And we don't want to increase it by less because then you'd have to constantly be calling resize. Another key thing to remember is because the hash function is so dependent on the number of buckets, because we're actually changing and increasing the number of buckets, we're going to have to also rehash all of the elements and put them into new sets of buckets. So yeah. We're talking a lot about hash functions and hash codes. So what exactly is a hash code? Well, there are a couple different types of hash codes. The first one is a valid hash code. A valid hash code has to be an integer. It has to be the same for each object, and it must be consistent. So it doesn't matter when, where, or how many times you call a hash code on a function, it always has to come up with the same one. And lastly, if two objects are equal, they have to have the same hash code. So if you call dot equal on two objects, it must return true if they have the same hash code. And vice versa, if they have the same hash code, they also have to be equal. So just because a hash code is valid, it does not necessarily mean that the hash code is good. So what makes a hash code good? A hash code is good if it distributes elements evenly. You could kind of think about it like if you're trying to spread cream cheese on your bagel, you want to spread out nice and even. You don't want to have too much cream cheese or too little cream cheese on a singular bite. A valid hash code can result in a lot of collisions, but a good and valid hash code minimizes the number of collisions and overflow entries. With this in mind, we're going to play a little fun game that I actually created. Very proud of myself for it. Extremely proud of the name, by the way. It's called Hash, Mash, or Pass. I know, really good. So a hash is a good and valid hash code. Mash is a valid but not so good hash code. And a pass, it's not even valid. I don't even want to see it in front of me right now. So let's remember what makes a good and valid hash code, and let's get right into it. So the first one is returning 2023. So is this a hash, mash, or a pass? Yes, this is going to be a mash. This is because it has all the qualities of a valid hash code, but because it's returning 2023 every single time, no matter what element we're calling it on, it's literally always going to result in collisions. So what this, let's say, hash map or hash set is going to look like, all of the buckets except one bucket is going to be empty, and in that bucket is going to be a really long linked list with however many elements we added to it. So it's not pretty, it's not the best, even though I guess it'll work. Moving on. This one is going to take the first letter of the word we're inserting and it's going to give it a numerical value. Hash, mash, or pass. This is also going to be a mash. Once again, it is valid, but let's say we have an example of where inserting a bunch of words starting with the same letter. It is once again going to result in many collisions, maybe not as much as the previous hash code we worked with, but still we could do better. So yeah, it's valid, but it's not good. Next one, we are returning the size. Size is basically referring to the number of elements in the hash map that we're using. So hash, mash, or pass. This is a pass. I don't want to see this in front of me. This is gross. This is disgusting. This would be the worst bagel I have ever eaten in my entire life. This is because size is always changing. Every time we add, insert, remove elements, size is going to be different. So if we call this hash code returning the size on the same element, it's not going to be consistent. We're going to get a different hash code every time. We don't like that. We like consistency. Lastly, hash code is going to return name.hashcode, hash, mash, or pass. This is going to be our hash. This is the most beautiful bagel I've ever eaten in my life. It's the most beautiful hash map, evenly distributed, so smooth, so beautiful to look at. I love it. This is Java's built-in string hash function. We know that it's going to give us a fairly unique hash code for most strings. We don't really need to know what's happening behind the scenes. Just know that Java's built-in hash code works. And lastly, we are going to do asymptotics for hashing. So worst case, if let's say we're returning that 2023 and results in a lot of collisions, it's going to be theta of n. So it's going to be proportional to the number of elements in that list because there's collisions every time. The best case is going to be theta of 1. This is perfectly evenly distributed. It's that best bagel. It's that Java built-in hash function. It is gorgeous, and it is constant time, which is what we are looking for. So it's the big takeaway. Runtime is based off how good your hash code is. Yeah. And that's about it for this video. If you guys have any questions, make sure to ask on Ed. And as always, good luck studying. I believe in y'all.